Scientific notation is a way of writing numbers that are too big or too small to be conveniently written in decimal form. Scientific notation has a number of useful properties and is commonly used in calculators and by scientists, mathematicians and engineers. In scientific notation, all numbers are written in the form a times 10 raised to the power of b, where the exponent b is an integer, and the coefficient a is any real number, called the significand or mantissa. The term mantissa may cause confusion, however, because it can also refer to the fractional part of the common logarithm. If the number is negative, then a minus sign precedes a decimal. Floating point is a computer arithmetic system closely related to scientific notation. Normalized notation: any given number can be written in the form or 10b in many ways. For example, 350 can be written as 3.5a, 102 or 35a, 101 or 350a, 100. In normalized scientific notation, the exponent b is chosen so that the absolute value of a remains at least 1 but less than 10. Thus 350 is written as 3.5a, 102. This form allows easy comparison of numbers, as the exponent b gives the number's order of magnitude. In normalized notation, the exponent b is negative for a number with absolute value between 0 and 1. The 10 and exponent are often omitted when the exponent is 0. Normalized scientific form is the typical form of expression of large numbers in many fields, unless an unnormalized form, such as engineering notation, is desired. Normalized scientific notation is often called exponential notation although the latter term is more general and also applies when is not restricted to the range 1 to 10 and to bases other than 10. Engineering notation. Engineering notation differs from normalized scientific notation in that the exponent b is restricted to multiples of 3. Consequently, the absolute value of a is in the range 1 per mole currency a 1000, rather than 1 per mole currency a 10. Though similar in concept, engineering notation is rarely called scientific notation. Engineering notation allows the numbers to explicitly match their corresponding SI prefixes, which facilitates reading and oral communication. For example, 12.5a, 10:09 am can be read as 12.5 nanometers, or written as 12.5 ANM, while its scientific notation equivalent 1.25a, 10:08 am would likely be read out as 1.25 times 10 to the negative 8 meters. Significant figures. A significant figure is a digit in a number that adds to its precision. This includes all non-zero numbers, zeros between significant digits, and zeros indicated to be significant. Leading and trailing zeros are not significant because they exist only to show the scale of the number. Therefore, 1,230,400 usually has 5 significant figures: 1, 2, 3, 0, and 4. The 2 zeros serve only as placeholders and add no precision to the original number. When a number is converted into normalized scientific notation, it is scaled down to a number between 1 and 10. All of the significant digits remain, but the placeholding zeros are no longer required. Thus 1,230,400 would become 1.2304x106. However, there is also the possibility that the number may be known to 6 or more significant figures, in which case the number would be shown as 1.23040x106. Thus, an additional advantage of scientific notation is that the number of significant figures is clearer. Estimated final digit, S. It is customary in scientific measurements to record all the definitely known digits from the measurements, and to estimate at least one additional digit if there is any information at all available to enable the observer to make an estimate. The resulting number contains more information than it would without that extra digit, S, and it may be considered a significant digit because it conveys some information leading to greater precision in measurements and in aggregations of measurements. Additional information about precision can be conveyed through additional notations. It is often useful to know how exact the final digit, S, are. For instance, the accepted value of the unit of elementary charge can properly be expressed as 1.6021764887, 40, A, 10 and 19 a C, which is shorthand for a, 10 and 19 a C, E notation. Most calculators and many computer programs present very large and very small results in scientific notation. Because superscripted exponents like 107 cannot always be conveniently displayed, the letter E or E is often used to represent times 10 raised to the power of and is followed by the value of the exponent. In other words, for any two real numbers A and B, the usage of AEB would indicate a value of AA, 10B. Note that in this usage the character E is not related to the mathematical constant E or the exponential function x. And though it stands for exponent, the notation is usually referred to as E notation or E notation, rather than exponential notation. The use of this notation is not encouraged in publications. Examples and other notations: in most programming languages, 6.022E23 or 6.022E23 is equivalent to 6.022A, 1023, and 1.6A, 1035 will be written 1.6E-35. Fortran also uses D to signify double precision numbers. The ALGOL60 programming language uses a subscript 1010 character instead of the letter E, for example, 6.02214151023. The ALGOL68 programming language has the choice of 4 characters, E, E, \, or 10. By examples, 6.0221415E23, 6.0221415E23, 6.0221415 or 6.02214151023. Decimal exponent symbol is part of the Unicode standard. For example, 6.0221415 it is included as U plus 23E8, a decimal exponent symbol to accommodate usage in the programming languages ALGOL60 and ALGOL68. The TI-83 series and TI-84 Plus series of calculators use a stylized E character to display decimal exponent and the 10 character to denote an equivalent operator, 7. The similar programming language requires the use of AND, for example, 6.0221415 and 23. Order of magnitude. Scientific notation also enables simpler order of magnitude comparisons. A proton's mass is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000can be obtained by comparing the exponents instead of the more error-prone task of counting the leading zeros. In this case, a 27 is larger than a 31 and therefore the proton is roughly 4 orders of magnitude more massive than the electron. Scientific notation also avoids misunderstandings due to regional differences in certain quantifiers, such as billion, which might indicate either 109 or 1012. In physics and astrophysics, the number of orders of magnitude between two numbers is sometimes referred to as dex, a contraction of decimal exponent. So for instance, if two numbers are within 1 dex of each other, then the ratio of the larger to the smaller number is less than 10. Fractional values can be used, so if within 0.5 dex, the ratio is less than, and so on. Use of spaces, in normalized scientific notation, in E notation, and in engineering notation, the space that is allowed only before and after A, or in front of E, or E is sometimes omitted, though it is less common to do so before the alphabetical character. Further examples of scientific notation: an electron's mass is about 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000.0093822A, 10^31 a kg. The Earth's mass is about 5973600000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 59736A, 1024 a kg. The Earth's circumference is approximately 40 million am. In scientific notation, this is 4a, 107 am. In engineering notation, this is written 40a, 106 am. In SI writing style, this may be written 40 ohm. An inch is defined as exactly 25.4 ohm. Quoting a value of 25.400 ohm shows that the value is correct to the nearest micrometer. An approximated value with only 3 significant digits would be 2.54a, 101 ohm instead. As there is no limit to the number of significant digits, the length of an inch could, if required, be written as 2.5400000000a, 101 ohm instead. Converting numbers. Converting a number in these cases means to either convert the number into scientific notation form, convert it back into decimal form, or to change the exponent part of the equation. None of these alter the actual number, only how it's expressed. Decimal to scientific. First, move the decimal separator point the required amount, n, to make the number's value within a desired range, between 1 and 10 for normalized notation. If the decimal was moved to the left, append (n). To the right, (n). To represent the number 1,230,400 in normalized scientific notation, the decimal separator would be moved 6 digits to the left and (106) appended, resulting in January 2304a, 106. The number -0.004a0321 would have its decimal separator shifted 3 digits to the right instead of the left and yield a 4.0321a, 10 as a result. Scientific to decimal. Converting a number from scientific notation to decimal notation, first remove the extra n on the end, then shift the decimal separator n digits to the right or left. The number 1.2304a, 106 would have its decimal separator shifted 6 digits to the right and become 1,234,400, while a 4.0321a, 10 would have its decimal separator moved 3 digits to the left and be -0.0040321. Exponential. Conversion between different scientific notation representations of the same number with different exponential values is achieved by performing opposite operations of multiplication or division by a power of 10 on the significand and subtraction or addition of 1 on the exponent part. The decimal separator and the significand are shifted x places to the left and 1x is added to the exponent, as shown below. 1.234a, 103 equals 12.34a, 102 equals 123.4a, 101 equals 1234. Basic operations, given two numbers in scientific notation. And multiplication and division are performed using the rules for operation with exponentiation. And some examples are: and addition and subtraction require the numbers to be represented using the same exponential part, so that the significand can be simply added or subtracted. Next, add or subtract the significands. An example: other bases. While base 10 is normally used for scientific notation, powers of other bases can be used too, base 2 being the next most commonly used one. For example, in base 2 scientific notation, the number 1001 in binary is written as 1.001a, 1011 using binary numbers, or, in E notation, 1.001e11, or, 1.125a, 23. This is closely related to the base 2 floating point representation commonly used in computer arithmetic. Engineering notation can be viewed as base 1000 scientific notation. See also, binary prefix, engineering notation, floating point, ISO 31-0, ISO 31-11, scientific pitch notation, significant figure, notes and references. External links: decimal to scientific notation converter, scientific notation to decimal converter, scientific notation in everyday life, an exercise in converting to and from scientific notation, scientific notation converter.